What's going on, everybody? This is Mr. Diamond. I'm going to turn up my audio a little bit because I think it was a little quiet. My mic is a little bit farther away from me than normal. But today we are going to be doing a Section 3 notes. We've up to this point talked about basics of equilibrium. We've talked about equilibrium expressions, but now we're going to get a little bit advanced with it. We're going to talk about ICE tables, or as they are sometimes called, Rice tables. You will see why in a little bit. Now that we have some basic KEQ calculations out of the way and kind of under our belt, we're going to move on to a more practical application. In reality, we might be able to measure all the pieces at the end of a reaction and solve for KEQ, but why would we do that? Because number one, we already have done the reaction, so we could just measure a lot of the information. Like if you wanted to know the KEQ, why are you doing the reaction to solve that? You could, number one, you could just look it up online and figure that out. But also, number two, you've already done the reaction. So if you were hoping to get something out of it, you've already done the reaction. You're not going to get anything else. So what if we could find something more useful with our KEQs? What if we could do something that was a little bit more beneficial using the same type of problems that we've talked about? What if instead of using our final stuff to find KEQ, what if I could tell you a KEQ and then tell you what you start with, and then you predict what you would have at the end of a reaction without needing to measure it? Now that sounds a lot more practical from like an industrial and an efficiency standpoint. If you're working in industry and you're trying to produce 25 grams of a substance, you don't want to just guess that. That costs money. Buying those chemicals is going to cost you a certain amount of money. And if you're wasteful, you're either, number one, going to lose money on the project or the process that you're doing, or number two, you're going to get fired because you're wasting money doing something. You want to try to be as efficient as possible. Now, sometimes efficiency takes different forms. For example, when I was a senior in college, I took a class where we actually talked about atom economics, which was trying to be the most efficient in involving how many atoms we are involving. And I feel like you're never going to actually use that unless you plan on literally working in industry. But this is a type of efficiency that is actually important, and it is something that is really practical to do. And it may seem a little bit scary, but it's really not that bad. So we're going to walk through a problem step by step and just work it out as an example, and then I'll kind of explain it in a little bit more detail. It says I'll go back and explain it, but I'll do that kind of at the end of this video. So our example that we have here is you have a mixture of 0.5 moles of H2 and 0.5 moles of I2. Both of them are in a 1 liter flask at 430 degrees Celsius, and they are reacting to form HI. And we know that it has a KEQ of 54.3, and we want to know what would be the concentrations at equilibrium of our iodine gas, our hydrogen gas, and our hydrogen iodide, or our hydroiodic acid. So we are going to switch on over to our hand cam, and I'm going to try to, as we work through this, I'm going to try to kind of explain a little bit of what I'm thinking as we go through here and why we're doing the pieces. But this is definitely going to be the type of question where you may need to come back later on and kind of ask me for clarification on why something is or what exactly we're doing. So obviously our first step that we're probably going to need, because this involves a reaction or a formula, is we are going to want to get our balanced equation. I apologize. I'm just digging for my calculator because I know I'm going to need it in a second. Okay, calculators acquired. I also had worked this out ahead of time, but I cannot find that sheet, and I don't feel like looking. I also a little bit crunched on time. I'm doing this right before I record a Zoom, or do a Zoom. So we'll work through it together, and I'll hopefully remember everything as I go. If not, you guys are all smart enough that you'll catch and ask questions for all the stupid things that I didn't explain. So we've got H2 as our first piece. We've got hydrogen, and we've got I2. We've got iodine. And it says we're going to form HI. It doesn't give any states of matter for anything, so that implies that we're probably not going to have to worry about it. In this specific case, I will let you know that these are all going to be... this is going to be one where we don't get to ignore anything, basically. I will tell you that our KEQ needs all three. We do need all three of the parts for it. Whether or not you want to consider them aqueous, solid, or aqueous or gases, it doesn't really matter for the purpose of this. So let's think about what's going to happen here. Well, we've got at the beginning, we've got 0.5 moles, but remember, all that we care about in our KEQ, if we write our expression for it, our KEQ, we normally put products on top, so we're going to put HI. Now, we didn't balance this. We've got 2 H's and 2 I's, so we do need to put a 2 there, which means this is going to get taken to the second power. And then on the bottom, we're going to have our H2, and we're going to have our I2. Okay, that seems pretty straightforward. That is our KEQ expression. I just realized my webcam is also out of focus. Man, we are just looking super unprofessional today. Let me try to get this a little more focused real quick. But while I do that, our next piece is, well, what do those brackets mean again? Well, those brackets mean molarity. So we actually need to convert our 0.500 moles into molarities. Molarities is moles divided by liters. In this case, thankfully, it is actually 1 liter, which means for both of them, we're going to have 0.500 big M molar. Now, at this point, you might go, well, I know a KEQ, and I know these two concentrations, so this doesn't seem that bad. I can just plug them in and solve for my unknown. But you don't know the equilibrium concentrations. The question says you have a mixture of 0.500 moles of H2, or in this case, you have 0.500 molar of H2 and 0.500 molar of I2. And this is at the start, not at equilibrium. So we actually need to figure out where it's going to end up at our equilibrium point. So to do this, we are going to set up our ice table. Now, this is going to be a little bit weird at the beginning, and I'll try to talk you through as best I can. But again, this is one that's like really weird to kind of try to teach digitally without you being able to ask questions as we go. So I'm going to start, and I'm going to write my H2. I'm going to leave a big gap. I'm going to write my I2. I used the wrong arrow up here. I hope some of you were yelling at me for that, because I was using the wrong arrow. I'm switching back and forth between chemistry and advanced chemistry mode. So we're going to use our double-headed arrow. And then over here, I've got 2HI. Now, what we're going to do first is we're going to list out what we have initially, or at the beginning. And this is our I of our ice table. We want our initial. So for H2, our initial concentration is 0.500 molar. And for I2, it is 0.500 molar. And then initially, we don't have anything of our hydrogen iodide. We don't have any HI at all to begin with. So that makes sense. The next piece of our ice table obviously starts with a C. So this is going to be our change. We want to know, how does it change throughout the course of this reaction? Well, some of you might be thinking, isn't that the question we're trying to answer here? We're trying to figure out what the change is. But we can kind of give it a little bit of guess. We won't actually know for sure at the moment what its change is. But we know that because these are all kind of in the same ratio of each other, that if this goes down by like some amount, we'll call that amount X. Let's say this goes down by some number of molars, some concentration amount of it drops. The same amount of iodine also has to go away. And then, because these are reacting together and these are going down, that has to go somewhere, and it's going to turn into our products over here. So we're going to put a plus on this side. However, there are 2 HIs formed for every 1 H2 or 1 I2 that reacts. So because these are both just a single X, but they only have a single 1 out front, this one's got a 2, so we're actually going to end up with twice the amount of HI as the amount of I2 or H2 that was lost. So again, this is not because there's two x's here. Do not think it's that. This number out front is based on the coefficient out front, because it's kind of like it's almost like doing a mole fraction. It's different than that, but it's almost like that's what we're doing here. So this is going to be two x's because our ratio up here tells us that. There's an invisible one here, an invisible one here, so there's nothing that goes with that. So that's our I, and that's our C, and then our E stands for equilibrium. So this is why it's an ice table. Now, sometimes I did mention it's called a rice table. That's just because the top can be called the reaction. So depending on what your professor says, they might say rice table or they might say ice table. But this is what we're setting up. We've got our reaction, we have our initial concentrations, we have what change they should go through. And now for our equilibrium. We don't know what X is, but we know that now our new concentration is 0.500 minus X. And our next one is 0.500 minus X. And then for our last one, for our product over here, 0 plus 2x is just going to be 2x. Okay, so this is going to be, we don't know what x is yet, but we now know what our concentrations should in general look like at the end of our process. Now we can take these values and plug them back into our KEQ expression. Now, just as a reminder, I'm going to rewrite it up here, and we'll need it in a second. The KEQ that it gave you in the problem was 54.3. So if we take these numbers, KEQ equals, first we're going to put our 2x, and then we square it, and then we divide that by 0.500 minus x times 0.500 minus x. Now, I was really nice in this problem, and I won't always be nice. In this problem, notice these two are the same things. We've got 0.500 minus x, 0.500 minus x. So what's another way you could write 0.5 minus x times 0.5 minus x? Well, if you're just doing the same thing multiplied by itself, this is the same thing as 0.500 minus x squared. And because of that fact, because of that being just the same thing, the same two pieces here, and the fact that we can square this, means that we can actually simplify our problem a lot, like a whole heck of a lot. It gets much harder if we have to do this. You actually are going to be having to do some distributions, and you may involve quadratic equations depending on what you're doing. So I hope you're all feeling good on your negative b plus or minus the square root b squared minus 4ac over 2a. But because these are all squareds, we can square root this entire side and square root this entire side. That's going to cancel both of our squares. And now if we plug our square root of 54.3 in, square root of 54.3, and enter. I thought that said it was 70 something. I was confused. Okay, so our square root of that is going to be 7.36885. And then that's also going to now be equal to 2x over 0.500 minus x. So next step, now we're kind of just in an algebra problem. Now we can just try to solve for our x. So we're going to take this whole piece, multiply both sides by our 0.5 minus x. We will get 7.36885 times 0.500 minus x equals 2x. We're going to distribute this to both pieces. So I'm gonna shorten it just so I can make sure it matches exactly what I have on my actual paper. So times 0.5, we will get 3.684425 minus 7.36885x equals 2x. Well, now we've got two separate x variables that we can combine together. So we're going to plus 7.36885. That gives us 3.684425. I know I'm writing these really long numbers. You don't have to write them this long when you do them, but I just want to make sure it's very clear of the numbers and where I'm getting them from. And then we're just adding 2 to this number. So it's just going to be 9.36885x. And now for our last step, we're going to divide each side by our 9.36885. 9.36885. And we get that x equals move this down so you can see it a little better. We get x equals 0.393263. But if we look back at our problem, all of our stuff has 3 sig figs, or at least everything we've used in the calculations. So we're going to do, this is 0.393. Now, the real kind of place that can trip people up with this is you might see this and you might go, okay, well, we're done. We just solved for x. But you didn't solve the question. The question, if I click back, we see that the question asks, what is the equilibrium concentration? So the problem does not care what the change is. It only wants to know what the end of this whole process is going to be. So now we take our x and we do our final, and this was a molarity. This is a change in molarity. So now we can take all of our pieces and we can finally put them together. So we've got H, we've got I2, and we've got HI. H2, if we look back up here at the end, it should be 0.5 minus 0.393. Our I2 is the same thing. It's 0.5 minus 0.393. And then our HI finally is going to be 2 times our 3.93, or 0.393. So plugging all these in our calculator just in case, because it's been a long day and I really don't trust myself to do this correctly, we get 0.107 molar, 0.107 molar, and then finally 2 times 0.393, 0.786 molar. So these values here, all of those values are our KEQ, or our equilibrium concentrations of each of the components in this reaction. With no knowledge whatsoever of what it was going to end up being, only with the beginning, only with the reactants, and knowing what they started with, you could use KEQ to predict this is the concentration of stuff that you should make, which again is a much more practical and much more useful application of this. Now, this process here, this step up here, is the same regardless of which side you have information on, regardless of if this side is 0 or not. It just makes this side, I apologize, I was off screen. If this side has zeros or doesn't have zeros, if these values are the same or if they're not the same, the only piece that changes, other than going through this process and kind of changing the coefficients out front, will be this math portion. This math portion could be as simple as what we did here. I know some of you might not think it's that simple, but it could be as simple as rearranging and just solving for a piece. It could be as complex as having to distribute pieces to each of the parts of this. I don't remember. I think it's distribution is the correct word for that. I might be wrong. It's been a while since I've taken math where I've needed to do that other than just for this problem. But you may have to distribute your questions. You may end up with a squared, and like an x squared, an x value, and a normal coefficient. And if that's the case, that means you're going to have to use your quadratic formula. So these can get a little complex, but really this process is the key player here, and this is the part where you should really be focusing your attention. I hope that makes sense. For the next couple of days, I'm going to give you a problem a day and then have the boxes so you can actually check your answers as you go through them. I'll be available on Zoom calls if you have any questions or if you want me to work out any examples or do any extra practice with you. I hope to try to have at least one, probably the first example for Monday. or for Tuesday will be one that is it does involve quadratic. I hope, and I will try to make sure that I'm on the Zoom call on Thursday or on Tuesday and on Friday to answer questions if you have anything about that. I hope that makes sense. I hope you have a great rest of your day. I hope to see/hear from you soon.